Hi, this is Baird Givens, and in this video, I'm going to show that the composition of continuous functions is continuous. And this is one of the places where the topological definition of continuity is really fantastic because it makes this proof incredibly easy, okay? Way easier than you would think. All right, so let's sort of rephrase it with more variables so that we have something to kind of write with, okay? So I can say, i.e., if f goes from x to y and g goes from y to z, if those are continuous functions, where x, y, and z are topological spaces, then h, which is the function g composed with f, so you start with f takes something from x to y, and then the output gets plugged into the g function and goes from y to z. So h goes from x to z is also continuous. Okay, so I have like my x here, and then I have my y here, and then I have my z here. And f goes from x to y, and g goes from y to z. And then h is the composition, which just jumps right over y and goes directly from x to z. Okay, so h just does f followed by g. And we write that as g circle f, g composed with f. Okay, so let's do the proof. Proof. I want to prove that h is continuous. So first I'm going to assume, I should write down my hypotheses carefully, assume f from x to y and g from y to z are continuous. Now I want to prove that h is continuous. The definition of continuity is that the inverse image of open sets or the pre-image of open sets are open. So I could start with an open subset of z and then prove its pre-image under h is also open in X, okay? And I could also do basic open or I could do closed because we've shown that there's like equivalent characterizations, but it's just as easy to use open here. There's really no reason to use one of these alternate characterizations, so let's just use the normal definition. So the normal definition of continuity is I start by taking an open set in the codomain. And so H, the codomain of H is Z. So I'm going to start with a U subset of Z and suppose U is open. So I'm going to start with a U over here. There's an open set. Okay. And I want to prove that H inverse of U is open. Where does H inverse of U live? So if I land in U, if I look at H, the H function goes from X to Z. So if I start with something Z and I want to look at its pre-image, that will be back up here in X. Okay. And I don't know enough about H to just do that in one step, but I do know that that G is continuous. And so if I start with, if I look at what hits U, well, G might hit U. So I can look at this set right here, G inverse of U. So since G is continuous, G inverse of U is open in Y. So I pull U back through the G function, backwards by the G function. So U is open, that means G inverse of U is open. Okay, but I want to keep pulling it back to X. So what function do I need to use to pull it back one more step? Yeah, G inverse of U is open. And so F inverse of any open set is open. So since F is continuous, F inverse of an open set, which is G inverse of U, is open in X. So here's my F inverse of G inverse of U. But that is H inverse, okay? That is H inverse. Finally, H inverse of U is the set of all little x and capital X such that H of little x is in U, which is the set of all little x in capital X such that G of f of x is in U, which is the set of all little x in capital X. Actually, I take it back. Let me just back up one step, which is the set of all, well, I want to say it's F inverse of G inverse of U. Is that obvious? Maybe it's not obvious. Maybe just let me do a couple more steps. Maybe it's obvious. If you think it's obvious, then you can stop watching the video now, and that's fantastic. Okay. I'm going to say this is G inverse. Ah, no, I know what I'm going to say. I got it. I got it. I got it. This is the set of all little x in capital X such that f of x is in G inverse of U. Okay, that's the meaning of being in G inverse of U is that G of U is in U. And then this is F inverse of G inverse of U. Okay, and so therefore H inverse of U is open in X. So to show that H is continuous, I started with an open set subset of Z, and then I showed that its inverse image under H was open in X, and that's the topological definition of continuity. Okay. We probably could have just said H inverse of U is equal to F inverse of G inverse of U without even going through those four lines to prove it. I might have thought that that was just obvious, and I'm still sort of thinks it might be obvious, but I think it was good to go through it a little bit more carefully. All right. Thank you for listening.